Okay, what we're going to do here is use the Generalized Stiffness Method to come up with then the stiffness matrix for this assemblage of three different members. Right? And so what we'll do then, since we have 8 degrees of freedom, is that one at a time we're going to impose a displacement at one of the degrees of freedom and then back out everything else that's going on. Right? So that means, for instance, we're going to let D1 for the first degree of freedom equal 1, and then all the rest of them, D2 will be 0, which is our so-called free degree of freedom, and then D3 will be 0. All of the rest of them will be held to be 0. And so let's get this drawn in here, what this would mean in terms of displacements. There's our unit displacement right there. And to go along with that are going to be a set of forces to make that happen. All right, so that's the displacement pattern that goes with that. And the displacements that are going to go with that, or rather the forces, in their positive sign convention sense, are going to be, we've got here's Q1 caused by that unit displacement at 1, Q then at 2, 1, and I'm going to show all of these in the positive direction. They may not turn out to be that way. And 2 more to go. Right, and so we're going to go through with this imposed set, figuring out what forces are necessary to impose to create this specific displacement pattern. And that means that when we get down to what we have down here, then we would have, once again, 1, 0, 0, 0, 2, 5, 6, 7, 8 entries there, and we'll have 8 forces that go along with that. And so that numerically what we'll have found are the stiffness coefficients in that first column, right? Because K11 times 1, then all the other 0 will give us this first one, etc., etc. So we're going to calculate the right-hand side that gives us then gives us at least one column, and then we'll do this 8 times, and we can get all 64, 8 times 8, of these stiffness coefficients. Right, so now the way that's going to work is we're going to want these axial stiffness values up here, the EA over L for each of the member, 320.4, 453.1, and then the 362.5 kips per inch. We're going to need all of that as we come down to deal with then each of these 3 members. Right, we're going to impose that displacement pattern, which means that, well, let's just work this out sort of through gut feel. This is a one-on-one member, so 45 degrees. So that means if the member end here, corresponding with degree of freedom 1, is 1 unit, that means its net elongation is going to be easy to figure out. Right? We just project that back onto its original axis, and so it will have elongated by 1 over the square root of 2, or 0.707 will be that delta. Right? And so there's an axial force that's necessary to have elongated that, and that axial force then would be N equal to that K times that delta. Right? And that K was for member 1, that's the 320.4. So there we go, 320.4 times, not 1 now, but times the reciprocal of the root 2, or 0.707, and that number is 226.6 kips. Right? And obviously you have to have an axial force down here at the bottom that's going to go along with that at 226.6.6, and then let's again divide by root 2 to get the components, and so we'll have, going to the left and going down, a 160.2. Right, now those are located directly at the Q41 and Q31 locations, and note they're both in the opposite directions of the positive sign convention. So if we carefully kind of partition this out here, then we should, I'm just going to rewrite this so it's a little bit bigger to see. we'd have minus 160.2 minus 160.2. That would be Q31 and Q41. Sorry, I should have meant to write that right here. There's those values right there. We'll put the brackets in after we're done. So that gets us those values. Now we come along and we do each of these members. So we come along and look at that one. That one goes over, and oh, that doesn't elongate or shorten at all. So we end up with then zeros here and there. Okay, so that means that Q51 is 0 and Q61 0. Right? Now some of you are saying, but hey, when it rotates over it elongates, but remember we go back to the original length. These are going to be so small that that angle would in reality be something like that much. Notice how little I'm turning that, very little, and so that extension we just in first order theory we ignore that. Right? So that member, nothing happens to that member other than it just fairly slightly displaces. And then we get to this last member, and let's see how that one works out. Once again, we're going to come out, oops, wrong color. I can't go back over that because that was the dark one. Right? So that's going to go out of unit 1, and then it's going to come back, swing it back, and that's going to be the short side of the 345, so that's going to be 0.6. This would technically be a 0.8 on this other side. That's how the 345 would work in this particular one. Notice this thing is more vertical than it is horizontal, meaning there's your 4, there's your 3, and so it's most like this one rather than that one. That means it's going to get the short side on the little displacement part. Right? So same thing we did before. Let's see, physically that's going to have shortened. So that axial force is coming downwards, and that's going to be then 0.6 times the axial stiffness of that member. Come back up at the top, that's 362.5 times 0.6, and that's 217.5 for the axial force. And then of course it's going to be down here as well, but we can break that up into components. The horizontal now will be the 0.6, so that's 130.5, and that's lined up with Q7 going in the opposite direction. And then we'll have the vertical component, that's 174. That is lined up with the positive direction, so Q81 would be 174. Right, now that's all but the last two. Right, in the last two then, well gee, okay, that involves all of these, but note that's just the equilibrium of everything, right? That Q21 has to be what's left over of the sum of these other four, and so that's not too bad to do. We've got a downwards 160.2 here, and upwards 174, the net being a 13.8 that has to go downwards there, so Q21 is going to be downwards 13.8, and Q11 will be then the net of all of these X components, 3, 1, 5, 1, and 7, 1. So there's the 130.5 is 0 and the 160.2. And so 130.5 plus the 160.2 would be 290.7, which should make sense, right? That's the same direction as what we were trying to move the forces, or as the force is the same direction as we're moving the displacement. So that makes sense that it should be a positive number, and then we can close off that bracket. And that is the same thing ultimately as this is KI1, the first column of the global stiffness matrix. Right? That's just degree of freedom 1. Hey, guess what? We got 7 more of these to do. We're not going to do all 7. We're going to do 2 more. to illustrate. And so degree of freedom 2 means that our displacement pattern is such that we are going to do just 1 unit displacement in degree of freedom 2, which is straight up. So there's your 1. And then we're not going to have any other displacements. Now we'll need forces to go along with that. So let's lay those out. We'll have Q22, Q at 1 caused by that unit load at 2. And then likewise 3 and 4 at our joint to the left, 5 and 6 down here in the middle, and then we have 7 and 8 right here. Right? These all go along with this very specific displacement pattern. Really, we could have superposed these on top of each other. I chose not to because I didn't want to make it any more confusing than it was already. Right? So let's get these written down here too. This would be Q at 1, 2, Q2 at 2, Q3, 2, Q4, 2, Q5, 2, Q6, 2, Q7, 2, and Q8, 2. And we're going to be finding then all of the KI2s ultimately. That's what we're doing. Right? So same kind of approach that we just did. And so we'll take this member here that's at 45 degrees, and we will now impose a unit displacement that is up, and so that once again is going to end up being 1 over root 2 for the elongation, and so it's actually going to have the same magnitude and in this case same direction of those values. Remember, 1 over root 2 is the elongation times the K for that member, which would have given us 226.6 for that one. And so that turns out then that Q3242 will once again be minus 160.2. These are all units of kips. Okay, so that's that one. Now, this one's easy because 1 unit of the system displacement at degree of freedom 2 will be exactly 1 unit of displacement for the that member. That's kind of interesting too. Now, I'm going to go ahead and draw this because I want to illustrate something that's going to turn out to be really kind of crucial later on. And that is something along the following. We have a 1 unit displacement that goes along with an axial force. Let's see, 1 unit, the stiffness value was 453.1. So 453.1 kips to get 1 inch of displacement. And so we get this 453.1 at the bottom. Well, that's Q52, so minus 453.1. But note something here. Oops, I'm sorry. That's not either. Q52 is to the side. That should be Q62. That Q52 is 0. Right? If it's not 0, this thing spins. It's pin connected on either end. And so that's a really important thing to take note of here. This global degree of freedom aligns perfectly with the local coordinate system, and things transverse to that aren't going to have any stiffness. That's going to come up again here in just a moment. No pun intended, with summing moments to verify that that's a 0 force. And then of course you got this last one that is at that 4-3 inclination for vertical. It's going to have 1 unit of deformation vertical, and that's going to be 0.8 elongation in this instant. Right? It's lying closer to the vertical, so it's going to get most of that. And so 0.8 times that stiffness, which is 362.5, is 290 for the axial force. It's elongating. So the components that we're going to end up with down at the bottom will be, let's see, 290 times 0.8, that's the vertical component, that's 232. Note how that 0.8 got in there twice, both at getting the displacement over here, finding the axial force, and then translating the axial force back into the global xy coordinates. That 0.8 got in there twice. That'll be really important when we look at the stiffness method, or direct stiffness method, that is. Right? And then we got the 290 times 0.6 to get the x component, that's 174. Okay. And that one lines up with the positive direction for 7.2, so that's 174, and the vertical is in the opposite, so that's a minus 232. And then what we got to do is we've got to get all, by summation of forces here in the x, Q22 will be the opposite of the sum of these others. They're all going downwards. So 232 plus 453.1 plus the 160.2 is 845.3. And then Q12, we've got nothing here in the middle. We've got 160.2 going to the right, 174 going, or sorry, to the left. We have a net of 13.8 going to the right, so we need something going back at 13.8 to the left. Which, lo and behold, that K12 value is going to be opposite, or sorry, is going to be exactly the same as K21 that we found for degree of freedom 1. Right? So again, generalized stiffness methods, we're just using equilibrium after imposing our displacement patterns, and of course the force displacement relationship going on. Now, here's this last one I want to do. We have to do this for all 8 of these, but let's look at degree of freedom 5 because it's kind of special. And that is, if we impose a unit displacement here and all the others are held 0, notice this is a pin connected member. We swing that out, it goes freely. That means that we actually have a rigid body mode here, that all of these are going to be 0 for that specific displacement pattern, and these being the forces that we have here for QI5. Rigid body mode associated with that particular thing. It takes no force to hold all these others to be 0 because it takes nothing to initially swing that out. There is no initial stiffness there. So that column, the 5th column, KI5 equals 0 for all I, and that represents a rigid body mode. We would eventually need to get rid of that series of equations in our system because we wouldn't be able to solve it simultaneously. We'd get a 0 on the main diagonal because of that rigid body mode that shows up. What that really kind of says is, if you go back to our original model, is that we really shouldn't have included that horizontal. We could have predicted this, that we should have reduced this down not to 8 kinematic degrees of freedom, but rather 7 would have been more appropriate. But we've got it all at least here. This it up. All right. So next, what we'll do is, well, how do we assemble all 64 of these? Yes, again, we'll have a bunch of zeros for some of them, but how would we do that in the direct approach, or the direct stiffness method?